All right, this video I'm going to go over the review for the interim. So in order to circumscribe a circle on a triangle, which line must you construct? Well, these are perpendicular bisectors. And remember that when we have a circle on the outside and the triangle on the inside, then this is a circumcenter. So the two things you need to remember here are perpendicular bisector and that is a circumcenter when we have perpendicular bisectors that create our center and our circle is circumscribed about the triangle. So when we talk about cross sections here, I want to talk to you about this cross section. It is perpendicular to the base, so it's a rectangle. This cross section is parallel to the base, so it is a circle. This one is, again, perpendicular to the base, so it is a rectangle. This one up here is going to go through this apex. Y'all notice this point up here? That's the apex. And so if we have a cross-section that goes through the apex of the cone, which would be the point that it comes to, then that is a triangle. And then again, if we go parallel to the base, we're going to have a circle again. This problem says find the height of the can of tennis balls. The volume of one tennis ball is 10.3 inches cubed. If a can of tennis balls has 3 balls, how high will the can be? So we are going to use the formula for the volume of a tennis ball to determine what the radius of the tennis ball is. So we're going to work through this here, put our 10.3 where our volume is. Then we're going to multiply both sides by 3/4 to get rid of the 4/3. That's going to get us here. Then we have to divide both sides by pi. When we do that, we get 2.46. Now what you should recall is that when we have an r to the third, the only way we get rid of that is to take it to the 1/3 power. So we have to take both sides to the 1/3 power. So now that's going to be r is equal to 1.35. Well, what I want you guys to notice here is that we have 1, 2, 3, 4, 5, 6 radii in that can of balls. So we're going to have to multiply 6 times that 1.35, and that tells us that the height of this can of tennis balls is 8.1 inches. Finding the volume of the sphere. Now, I can almost guarantee y'all that the volume of the sphere is going to be on here because the most common mistake is that people square the radius instead of cubing the radius. So be careful and make sure that you are cubing the radius. And also notice, because that line is drawn all the way across the sphere, that 42 is a diameter. It's not our radius. So we're going to have to divide that by 2 first before we do the problem. And then also watch when you guys are doing these problems to see if pi is in your answer or not. Because those are two different answers based on whether pi is in the answer or not. This one then says find the volume of the image. So what I'm going to do is find the volume of the whole image by doing length times width times height. That's what I'm going to do first. So that's going to give me 22,800. Then I'm going to find the volume of this area right here. So we got our length times width, and then right there, yeah. So this whole thing up here was 38, so I'm going to subtract 20 from it because I got my 10 here, my 10 here. So that's how I got the 18 here. So when I find the volume of this area right here, or that box in essence, I'm going to multiply 18 times my 15, that was my depth here, times my 12. And then I'm going to find half of a cylinder right here. So notice again that if I go this far, that's my diameter, so my radius would be 9. And then I'm going to have my height, which would be this 15 here. So that I'm going to do, and then, so it's going to be pi r squared times the height, but I'm going to take half of that. So that's going to be 1908.5. So then I'm going to add those two together, the 3240 plus the 1908.5, and subtract them from the 22,800. So the answer here was 17,651.5, again, feet. This should be cubed, sorry. Cubed because that's volume. Sorry, my guys. Sorry. That should have been cubed because that's volume. All right, so how does the volume of the cone relate to the volume of the cylinder? These are the kinds of questions that you guys need to be fully prepared for, because this is like, how do we derive the equation of a cone if the base and the height of a cylinder are the same? And all of us should know that the cone is 1/3 of the cylinder. So it takes 3 cones, volumes, or to fill up that cone, would take 3 times of filling it up to fill up that cylinder that has the same radius and height. Conversely, it says, how does the volume of the square prism relate to the volume of the square pyramid? So again, here we're talking about this area of the base and this area of the base would be the same, and their heights would be the same. So this time we'd have to multiply 3 times that square pyramid to get the volume of the square prism. Here's our next one. We're going to talk about area density. Area density says how many people can we fit in a certain area. So we're going to take our people over our area. So that's going to be 20 over 5 times 5. So that's 20 over 25. And this could be reduced to be 4/5 if we wanted to. Okay. Then the question is, if we know that that's our population density, then how many people could we fit with the same population density in an area that was 500 feet by 500 feet? So we could leave it as it was here, 20 over 25, or we could make this 4/5. Either way, we're going to ultimately cross multiply this to get our answer. So we're going to multiply 25 times x and 20 times 250. And when we do that, we're going to get that x equals 200,000. So at the same square footage per person, we could fit 200,000 people in a 500 by 500 foot square. Then we're talking about volume density. Now, I really want to show y'all this because most of y'all would not even know that this is talking about density by reading this question. So it says a sphere gas tank has the dimensions showed when filled with gas to provide 117,500 BTUs of energy. To the nearest 10 BTUs, how much energy does 1 cubic foot of the gas yield? Well, it's saying energy per cubic foot. So that's one of my hints that this is a density problem. So I need to be able to find the mass and the volume. Well, the mass is the 117,500. The volume we would find by the equation 4/3 pi r cubed. Once again, notice that we have the diameter, not the radius, so we're going to have to divide that by 2 first. So we're going to cube the 3, multiply it times pi times 4/3. That gets us 113.10. Then we're going to get the density by dividing that mass, the 117,500, by the 113.10. When we do that, we get 1038.9, but it tells us up here to get the answer to the nearest 10 BTU, so we're going to round that to 1040. And again, the fact that this has got 2 measures here, BTUs per feet cubed, that's what kind of gives me a hint that this is density. This next one says, Sarah has completed the first few steps in constructing the inscribed circle. So inscribed circle means that we're drawing the circle inside here, right? And I know that doesn't look like a perfect circle, but y'all get my drift. So inscribed inside, that has to do with an in-center. And what do we use to draw in-centers? We use angle bisectors. So once again, those are the things you need to keep in mind. In-center, inscribed, angle bisectors. So this one says 2 tangents intersect outside a circle. So I'm going to go ahead and draw 2 tangents that intersect outside my circle here at some point, right? So to find the length of these tangents, we would set them equal to each other. So that's our formula, tangent equals tangent. For this next one, we have a tangent and a radius that intersect. So we have a tangent here and we have a radius here. So recall once again that there's a right angle there, right? So also recall that this radius and this radius have to be congruent. Those are the things you need to keep in mind. And we would use the Pythagorean theorem again to solve for missing sides when we have a tangent and a radius that intersect. Then we have a chord and a diameter that intersect. So, and we're going to say that these intersect at a right angle, okay? So if there's a right angle here, then that means that that chord is being bisected by that diameter or that radius. And once again, remember that we have a right triangle there, so we once again can use Pythagorean's theorem to solve for missing pieces. This next one says 2 chords intersect inside a circle. So what does that look like? That looks like this. And again, we're talking about from here to there and from there to the center. So from the circle to the center, from the circle to the center. So these are part times part equals part times part. And if you recall, when I taught my class this, we did part times part equals part times part. The next one says two secants intersect outside a circle. So when we have two secants that intersect outside a circle, it looks like this. And when we do that, we're going to do our outside part times our whole. So we're going to take this part right here times the whole thing, and this part right here, again, times the whole thing. Got it? So outside times whole equals outside times whole. A tangent and a secant intersect outside a circle. So this one we have a tangent up here, and we have a secant down here. Hopefully you remember with this one, when we have the tangent, we're going to square it. And we're still going to deal with our secant the same way with the outside times the whole. Now this one, we have a circle here that has a radius of 5, goes from the center of the circle to a point on the circle. And this is how they derived the equation of a circle. Notice that that right triangle in there, the hypotenuse of that right triangle is also the radius of the circle. So we're going to use a squared plus b squared equals c squared, right? Well, notice here that if we want to find this, this is our center right here, and this is our h and k. And that should take you back to the equation of a circle. And then we have x and y. Well, x and y are just a point on the circle. So if we were to solve for the radius of the circle, we could do that by plugging in these values. So now, here our center was 0, 0, right? So this would have been 0 minus, or sorry, this would have been, yeah, 3. 3 minus 0 squared plus 4 minus 0 squared equals r squared, right? Well, that's going to be 3 squared plus 4 squared. That's 9 plus 16. That's 25, right? Well, guess what? That's exactly what my radius is, because this r squared would be 5 squared, right? 5 squared is 25. So that's how we get the equation of a circle. And when we're trying to find r, remember that's what I just did here. I solve for the radius by plugging in the center and a point on the circle to get the radius. Also note that if you are given a point and they ask you, is it on the circle, you can plug it into the equation of the circle. And if the equation is equal, then we know that that point is on the circle. If it's not, then the point is not on the circle. This one right here, we have two circles. So it says, what is the equation of the blue circle? Well, the center over here for the blue one is 5, negative 5. And our radius is 1, 2, 3, 4. So the radius is equal to 4. So this equation is x minus 5 squared plus y. Now I'm subtracting a negative here, so that's going to be plus 5 squared. And then this is equal to r squared, which would be 4 squared. That would be 16. Our next one is the red circle. And the red circle has, it's at negative 5, negative 2. That's our center for that one. And our radius here is 2. So when we talk about this one, it says, what is the equation of the red circle? This one is going to be x plus 5 squared plus y plus 2 squared. And again, we're going to square that 2, so this is going to be 4. Now the next question this asks us is, what transformed the blue circle to the red circle? Well, let's take our ending radius, which is 2, over our beginning radius, which is 4. So you should be able to see that this was reduced by a scale factor of 1/2. But then also, if it was just reduced, then our center would not have changed, and our center did change. So let's count how much. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it moved 10 to the left, right? And then it moved 1, 2, 3 up. So that would be my vector right there that would have moved it. So it would have moved 10 to the left and 3 up. This one says complete the square to find the center and the radius of a circle given by the equation x squared plus y squared minus 6x minus 4y minus 6 equals 0. So when we do this, we want to group our x terms and our y terms in parentheses first. And then we're also going to move that constant to the other side of the equal sign. Then what we're going to do is we're going to divide the 6 by 2 and that negative 4 by 2, and we're going to drop those into our parentheses. Now, also what we're going to do is we're going to square this 3, put it back up here. And remember, if we add to the left, we got to add to the right. Going to square this negative 2, that's a 4. Again, going to add that up here. So this is how I got 19 right here. Then the question is going to ask us, what is the center and the radius of this? So remember, the equation is x minus h squared, y minus k squared. So our center here is going to be opposite of what's given there. So that's going to be negative 3, positive 2. And this right here is r squared. So r squared equals 19. So that means r must be equal to the square root of 19. So when we have a quadrilateral inscribed inside a circle, we should know that opposite angles are supplementary. So when I add the x to the 108, that should equal 180. And when I add the 88 to the y, that should also equal 180. So recall again that when a quadrilateral is inscribed inside a circle, that opposite angles are supplementary. This one says, how long would a string of lights need to be to go around the outside circle of this Ferris wheel? Well, that's just using the circumference. So we use 2 pi r. That's 63 pi. And then if we were to multiply 63 by pi, we get 197.9 feet. Well, my question for y'all too is, what if that Ferris wheel fell off of the brace holding it, that triangle holding it, and it rolled 3 times? Well, that would be the distance that it would travel. We would have to multiply this by 3. And that would tell us the distance it would travel if it fell off of its brace and rolled 3 times. And you need to be able to think through that kind of stuff when it comes to circumference. Then we have a central angle and intercepted arc. So remember again that a central angle is an angle whose vertex is at the center of the circle. And central angles are equal to their intercepted arcs. An intercepted arc is an arc that basically is out here. It basically is the arc that closes in the angle. An inscribed angle is an arc that subtends. Here's an inscribed angle. Now with this one, we have again an arc that subtends it. So if this arc was 100 degrees, then this angle would be 50 degrees. If the angle was 50, obviously the arc would be 100. So with the relationship we're dealing with here is the inscribed angle is half the subtended arc. The subtended arc is 2 times the inscribed angle. Then we're talking about an angle that's formed by 2 chords that intersect inside a circle. So here we have 2 chords that are intersecting, right? We're talking about this angle right here. So to get this one, we're going to add the arc plus the arc and divide it by 2. That's how we're going to get our angle. Our next one says an angle formed when a tangent and a chord intersect. So I got a tangent right here, and then I got a chord. So here again, if I told y'all that this was 60 degrees, then my arc right here would be twice it. That would be 120. Well, if this was 60, we got a line here, remember, so that would be 120 out right here, right? Because those two added together should equal 180. And then this arc out here, the other arc out here would be 2 times 120, which would be 240. And recall again that our whole circle has to equal 360 degrees. So these are some of the relationships we need to use here, that the angle is half the arc is 2 times the angle, the circle's 360 degrees, and the line's 180 degrees. Then we have an angle formed when a chord and a diameter intersect. So here we go again. We've got a chord and a diameter. Now, if we know that these are congruent, it bisects it, then we know that it's here at a right angle, right? And we know that we can use, again, Pythagorean's theorem to solve because we have a right triangle there. Remember also that all radii in a circle are congruent. Then we have an angle formed when 2 secants intersect outside a circle. So we've got a secant there, and we got a secant here, and we're looking for this angle. Recall with this one, we're doing outside arc minus inside arc divided by 2 equals the angle. The next one has to do with an angle formed with a tangent in a secant. So here we go again. We got a tangent here, and then we got a secant. Well, the process is the same. We still have an outside arc minus an inside arc divided by 2. That equals the angle. And here's our last one, 2 tangents. Now this one's a little tricky sometimes, only because it only touches our circle at one point. So if we're looking for this angle in here, then, and we know that, let's just say that this was 120, then the way that we would find this outside arc is to go 360 minus 120, and that would be 240. That's how we would find our outside arc. So once again, though, we would do outside arc minus inside arc, right? Sorry, they meet all the way. Outside arc, so this would be 240 minus 120. That would be 120 divided by 2, which would be 60. So that angle would have been 60 degrees there based on the numbers that I threw into this problem. Then we want to find this area of the sector. So you guys, with these types of problems, you need to really read the problems, and also notice that this has pi in the answer. So I'm not going to multiply by pi. This is the formula that's on the formula sheet, which is pi r squared theta over 360. Theta is our angle of our central, or our arc, either one. Could be either one of those. This is to leave in terms of pi, so I'm not going to multiply by that pi right there. I'm going to leave it, and I'm just going to do 8 squared times 120 divided by 360. Once again, make sure you guys read these problems. Determine whether it's asking you about arc length or sector area, and use the appropriate formula. Last one I want to go over here is finding the area of the segment of a sector. So we're looking for this green area right here, the green area. So to do that, we're going to find the area of the sector, and we're going to subtract from it the area of the triangle. So we're going to use pi r squared theta over 360, and then we're going to subtract from it 1/2 our base times our height. And remember, this would be 4 over here as well, because it's just another radii, right? So once we do that, we get 12.57 for this number, and then we get 8 here because half of 16 is 8. So this would be 4.57 meters squared.